Hello friends, in our last discussion we talked about the center of mass of a system of particles and learned that the center of mass of a system of particles is the point that moves as though all of the system's mass were concentrated there and all external forces were applied there. We dealt with some of the sample problems as well. In today's discussion, we shall be talking about the Newton's second law for a system of particles. Now that we know how to locate the center of mass of a system of particles, we discuss how external forces can move a center of mass. Let us start with a simple system of billiard balls. If you roll a cue ball at a second billiards ball that is at rest, you expect that the two ball system will continue to have some forward motion after impact. You would be surprised, for example, if both balls come back towards you or if both moved to the right or to the left. What continues to move forward, its steady motion completely unaffected by the collision, is the center of mass of the two ball system. If you focus on this point, which is always halfway between these bodies because they have identical masses, you can easily convince yourself by trial at the billiard table that this is so. No matter whether the collision is glancing head on or somewhere in between, the center of mass continues to move forward as if the collision had never occurred. Center of mass in motion. To understand the center of mass in motion, we replace the pair of billiard balls with an assemblage of n particles of possibly different masses. We are interested not in the individual motions of these particles, but also in the motion of the center of mass of the assemblage. Although the center of mass is just a point, it moves like a particle whose mass is equal to the total mass of the system. We can assign a position, a velocity and acceleration to it. We state, and we shall prove it next, that the vector equation that governs the motion of the center of mass of such a system of particles is F net is equal to m a com. The equation is Newton's second law of motion of the center of mass of a system of particles. Note that its form is the same as the form of the equation for the motion of a single particle. However, the three quantities that appear in equation must be evaluated with some care. First, F net is the net force of all external forces that act on the system. Forces on one part of the system from another part of the system, that is internal forces, are not included in this equation. Second, m is the total mass of the system. We assume that no mass enters or leaves the system as it moves, so that m remains constant. The system is said to be closed. Third, a com is the acceleration of the center of mass of the system. This equation gives no information about the acceleration of any other point of the system. The equation is equivalent to three equations involving the components of F net and A com and along the three coordinate axes. These equations are F net x is equal to m a com x, F net y is equal to m a com y, F net z is equal to m a com z. Now, we can go back and examine the behavior of the billiard balls. Once the cue ball has begun to roll, no external force acts on the two ball system. Thus, because F net is equal to 0, equation A tells us that A com is 0 also. Because acceleration is the rate of change of velocity, we conclude that the velocity of the center of mass of the system of two balls does not change. When the two balls collide, the force that comes into play are internal forces on one ball from the other. Such forces do not contribute to the net force, which remains 0. Thus, the center of mass of the system, which was moving forward before the collision, must continue to move forward after the collision with the same speed and in the same direction. Motion of the center of mass of solid body. Equation A applies not only to a system of particles, but also to a solid body such as the bat as shown here. We know F net is equal to m a com. M in equation A in this case is the mass of the bat and F net is the gravitational force on the bat. The equation tells us that a com is equal to g. In other words, the center of mass of the bat moves as if the bat were a single particle of mass m, with force F net acting on it. Motion of the center of mass of fragments. Figure here shows another interesting case. Suppose that at a fireworks display, a rocket is launched on a parabolic path. At a certain point, it explodes into fragments. If the explosion had not occurred, the rocket would have continued along the trajectory. The force of explosion are internal to the system. That is, at first the system is just the rocket and later it is in its fragments. That is, they are forces on parts of the system from other parts. If we ignore air drag, the net external force F net acting on the system is the gravitational force on the system regardless of whether the rocket explodes. Thus, from equation A, the acceleration a com of the center of mass of the fragments while they are in flight remains equal to g, the gravitational pull. This means that the center of mass of the fragments follow the same parabolic trajectory that the rocket would have followed had it not exploded. Proof of vector equation governing the motion of the center of mass. When we define the center of mass with the language of vectors, the three scalar equations identified by three coordinates can be replaced by a single vector equation as shown here, where r com is equal to 1 upon m sigma mi into ri. Here m is the total mass of the system and r com is the vector locating the position of the system's center of mass. I varies from 1 to n. Now, for a system of n particles, mr com is equal to m1 r1 plus m2 r2 plus m3 r3 so on up to mn rn. Here m is the system's total mass and r com is the vector locating the position of the system's center of mass. Differentiating the equation with respect to time gives m v com is equal to m1 v1 plus m2 v2 plus m3 v3 and so on up to mn vn. Here vi is the velocity of the ith particle and v com is the velocity of the center of mass. Differentiating this equation with respect to time gives ma com is equal to m1 a1 plus m2 a2 plus m3 a3 and so on up to mn an. Here ai is the acceleration of the ith particle and a com is the acceleration of the center of mass. Although the center of mass is just a geometrical point, it has a position, a velocity and acceleration as if it were a particle. From Newton's second law, MIAI is equal to the resultant force F1 that acts on the ith particle. Thus, we can rewrite the above equation as MACOM is equal to F1 plus F2 plus F3 and so on up to Fn. Among the forces that contribute to the right side of the equation will be forces that the particles of the system exert on each other and forces exerted on the particles from outside the system. By Newton's third law, the internal forces form third law force pairs and cancel out in the sum that appears on the right side of the equation. What remains is the vector sum of all the external forces that act on the system. This equation then reduces to equation A, the relation that we set out to prove, that is F net is equal to MA com. Linear momentum. In this section, we discuss only a single particle instead of a system of particles in order to define two important quantities. The first definition concerns a familiar word, that is momentum, that has several meanings in everyday language, but only a single precise meaning in physics and engineering. The linear momentum of a particle is a vector quantity that is defined as P is equal to m into v. Here m is the mass of the particle and v is its velocity. Since m is always a positive scalar quantity, equation tells us that p and v have the same direction. The SI unit for momentum is the kilogram meter per second. Newton expressed his second law of motion in terms of momentum as the time rate of change of momentum of particle is equal to the net force acting on the particle and is in the direction of that force. We can represent this in equation form as F net is equal to dP upon dt. In words, we say that the net external force on a particle changes the particle's linear momentum. Conversely, the linear momentum can be changed only by a net external force. If there is no net external force, linear momentum P cannot change. Substituting value of P is equal to mv into this equation for constant mass m, we get F net is equal to d upon dt into mv and is again equal to m dv upon dt and finally is equal to m into a. Thus, the relations F net is equal to dP upon dt and F net is equal to ma are equivalent expressions of Newton's second law of motion for a particle. The linear momentum of a system of particles. In this section, we extend the definition of linear momentum to a system of particles. Consider a system of n particles, each with its own mass, velocity and linear momentum. The particles may interact with each other and external forces may act on them. The system as a whole has a total linear momentum which is defined to be the vector sum of the individual particles' linear momentum. Thus, P is equal to P1 plus P2 plus P3 and so on up to Pn and is equal to M1 into V1 plus M2 V2 plus M3 V3 and so on up to mn vn. And another way we can define this linear momentum of a system of particles is through this equation, where P is equal to mv com. In words, we can say that the linear momentum of a system of particles is equal to the product of the total mass m of the system and the velocity of the center of mass. Now, if we take time derivative of this equation, we find dp upon dt is equal to m dv com upon dt, and we know dv upon dt is acceleration. Therefore, dp upon dt is equal to m a com. Now, compare this equation with equation of Newton's second law for the motion of the center of mass of a system of particles. F net is equal to m a com. Comparing these equations, we find that F net is equal to dp upon dt. Here, F net is the net external force acting on the system. This equation is a generalization of the single particle equation to a system of many particles. In words, the equation says that the net external force on a system of particles changes the linear momentum of the system. Conversely, the linear momentum can be changed only by a net external force. If there is no net external force, linear momentum cannot change. So, friends, here we come to the end of our discussion, and therefore, we sum up. In this lecture, we learned that the motion of the center of mass of any system of particles is governed by Newton's second law for a system of particles, which is F net is equal to m a com. Here, F net is the net force of all the external forces acting on the system. M is the total mass of the system, and a com is the acceleration of the system's center of mass. For a single particle, we define a quantity p called its linear momentum as p is equal to m into v, and can write Newton's second law in terms of this momentum as F net is equal to dp upon dt. For a system of particles, these relations become p is equal to mv com and F net is equal to dp upon dt. So, that is it for today. In the next lecture, we shall be discussing about collision and impulse and conservation of linear momentum. Thank you very much.